dia itu terdistribusi dalam bentuk volume seperti ini, maka di sini dV begitu ya. Kita dapatkan di sini bahwa namanya dV, kita integralkan ini kalau luasannya seperti itu. Kemudian kita inginkan bahwa di dalam medan elektrostatik itu sifatnya irrotasional, sehingga curl-nya itu sama dengan 0 gitu ya. Curl-nya sama dengan 0. Kemudian ada istilahnya adalah flux, yaitu jumlah garis gaya yang melewati luasan tertentu yang kita namakan sebagai flux-nya. Kalau hukum Gauss itu menyatakan bahwa integral tertutup ya dari sama dengan jumlah muatan yang terlingkupi. Tapi kita perhatikan di sini dengan medan listrik dari suatu muatan dinyatakan seperti ini ya, E sama dengan 1/4 V epsilon 0 I per R kuadrat. Nah, demikian pula kita ketahui bahwa kalau dia ini muatan positif, maka medan listriknya ke arah radial seperti ini ya. Jadi Anda lihat seperti itu. Nah, sedangkan kalau ini ada muatan positif, ini ada muatan negatif, maka ada garis-garis ini yang kita namakan sebagai ekipotensial. Nah, titik kalau misalkan ini di sini ada biasanya ini kita gunakan eksperimennya eksperimen geolistrik ya, jarak antar satu dengan tempat lain kan agak jauh, maka dianggap bahwa di sini muatan positif, di sini muatan negatif, sehingga bagaimana perhitungan terhadap resistivitas di dalam di bawah itu daerah ekipotensial ya. Sebagaimana juga eksperimen di elektrokapasitif cancer terapi itu memanfaatkan elektroda yang muatan positif dan negatif yang dimodulasi sehingga kita bisa mendapatkan bagaimana organ-organ di dalam tubuh manusia. Ya. Ini kalau dia muatannya sama positifnya seperti ini. Dan ini kita ketahui bahwa kalau garis gaya listrik itu mengenai pada luasan tertentu, maka ini dinamakan sebagai flux. Ya, nilai fluxnya itu sama dengan E dot dA. Dan tadi saya katakan bahwa dA itu selalu tegak lurus di permukaannya. Jadi ini yang kita namakan the flux of A. It measure the number of feet line ya passing through S is equal ada luasannya. Ya, ini kita dapatkan seperti itu. Ya, ini Gauss law-nya bisa kita sebutkan sama. Jadi integral tertutup D dot dA sama dengan jumlah muatan yang terlingkupi. Ya, ini kalau dia jadi integral tertutup E dot dE sama dengan Q enclosed. Ya, enclosed itu artinya yang terlingkupi. Jadi jumlah garis bahaya yang melitu pada luasan Gauss itu sama dengan jumlah atau muatan Gauss yang dilingkupi. Coba kita lihat ini itu ada video ya, sebentar saya carikan dulu. Nah, oke, ini coba kita lihat.
Imagine if we have a surface with an electric field emanating out of the surface.
Jadi ini tanda merah itu menandakan arah
surface has an area which
arah
we'll call
permukaan. Ya,
Phi is the angle between a normal line and electric field. Because the normal line and electric field are parallel to each other, the angle phi is equal to 0. and cosine 0 is 1. Now, what if the electric field is not perpendicular to the surface? What happens in that case? So let's draw the normal line. And here's the line parallel to the surface. And let's say the electric field is at an angle. So this is the angle phi, this is the angle theta. So phi is between the normal line and the electric field vector. In this case, the electric flux is going to be equal to EA cosine phi. The electric flux has its maximum value when this.
Ini kalau misalkan luasannya itu seperti ini ya. Ini tadi dia di sini menulis EI. Fluxnya tadi sebenarnya ya flux sama kayak tanda flux.
Angle is 0. Now what happens if the electric field vector is parallel to the surface or perpendicular to the normal line? So let's say the electric field vector is here. In this case, the angle between the normal line and the electric field is 90. The electric flux is equal to EA cosine phi. Cosine 90 is equal to 0. So the electric flux is 0 in this case. Let's try this problem. What is the electric flux through a sphere of radius 4 meters that contains a 50 microcoulomb charge and a negative 50 microcoulomb charge at its center? So let's draw a picture. So here we have a sphere, and there's a positive charge inside the sphere. Now the electric field will always be perpendicular to the surface. So the flux is simply the electric field times the area. In the case of a sphere, it's always perpendicular to the surface. So it's going to be E times A, where A is the surface area of a sphere. So let's say the sphere has a radius r. The surface area is going to be 4 pi times r squared. Now the electric field produced by a sphere, you can treat it as if it's a point charge, particularly if you want to calculate the electric field outside of a sphere. And so that's equal to K times Q, which is the charge in the sphere, divided by r squared. So notice that we can cancel r squared. And K is 1 over 4 pi times epsilon sub naught. So we can also cancel the 4 pi. So therefore, the electric flux in the sphere is equal to the charge enclosed by the sphere divided by epsilon sub naught. This equation is basically associated with Gauss's law, which states that the electric flux is proportional to the charge enclosed by the object. So it's just going to be 50 times 10 to the minus 6 divided by 8.85 times 10 to the minus 12. So you should get 5.65 times 10 to the 6th power newtons times square meters per coulomb. So that's the electric flux. Now here's the question for you. Is the answer positive or negative? The answer is positive because if you place a positive charge inside a sphere, the electric flux is an outward flux. For part B, the magnitude is the same. But if you put a negative charge inside the sphere, then the electric field enters the sphere. So we have a negative inward electric flux. So the answer for part B is the same value, but negative 5.65 instead of positive 5.65. Now let's say if we have a horizontal disk. Let me draw it better. And it's the shape of a circle, And this disc has a radius of, let's say, 3 meters. Here's the normal line. And let's say the electric field is in this direction. It passes through the disc all throughout the surface of the disc, but in that direction. The angle between the electric field vector and the plane of the disc, let's say, is 30 degrees. Calculate the flux, the electric flux passing through the surface. Feel free to pause the video. And let's say the electric field, let's give it a value of 100 newtons per coulomb. So the electric flux is equal to the electric field times the area of the disc times cosine of phi. Now the angle that we have is theta, not phi. Phi is this angle, it's the complementary angle. So phi is going to be 90 minus 30, so it's 60 degrees. The area of the disc is pi r squared. So this is going to be E times pi r squared times cosine phi. The electric field is 100. R squared is 9, 3 squared is 9. And then cosine 60. Cosine 60 is 1/2. And 100 times 9 is 900. Half of 900 is 450. So the electric flux is 450 pi. So this is the answer. Now let's try another problem. So let's say if we have a cube that looks like this, and we're going to place a positive charge at the center of the cube. What is the total electric flux that emanates outside of the cube? How can we calculate the total electric flux? Now, for a problem like this, you don't want to find the electric field that passes through each surface. That's going to be difficult because in some areas, the electric field will be at an angle. And so that's going to be very difficult. The best way to answer this problem is to use Gauss's law, where the electric flux is simply equal to the charge that is enclosed by the surface divided by epsilon sub naught. This equation makes these problems a lot easier to solve. So let's say the charge is 30 microcoulombs. So all you got to do is take the 30 microcoulomb charge, which is 30 times 10 to the minus 6, and divide it by epsilon sub naught. So that's going to give you the total electric flux that passes through the cube. And this is an outward electric flux, so the answer is positive. So you should get 3.39 times 10 to the 6. So that's the electric flux. Now, what if we wanted to calculate the electric flux through one of the 6 faces in the cube? If you need to do that, simply multiply your answer by 1/6 or divide it by 6. So the electric flux that passes through each surface or each face of the cube is 5.65 times 10 to the 5 newtons times square meters per coulomb. Now let's draw another cube. So this time, there's not going to be any charge inside the cube. Now the length of each side of the cube is 3 meters. And let's say that there's an electric field that passes through this sphere, from the bottom face to the top face. And let's say the electric field is also perpendicular to the plane of the top part of the cube and the bottom part of the cube, which means that it's parallel to the normal line. So what is the electric flux through this object? How would you calculate it? So the electric flux on the right side and on the left side is 0 because it's not perpendicular to the plane of those sides. The electric flux in the front and in the back is also 0. Now, what about the top and the bottom face? What is the electric flux in those regions? So let's focus on the top part. The electric flux that passes through it is going to be the product of E times the area of that surface. So it's going to be positive EA. The reason why it's positive is because the electric field is leaving the closed object. It's escaping from it. So it's an outward flux. So it's positive. Now what about the bottom surface? Notice that the electric field vector enters the object. So it's an inward flux. So the electric flux is E times A, but it's going to be negative EA. So to find the total electric flux is the sum of these two values. Positive EA and negative EA, they cancel. And so the net electric flux is therefore equal to 0. Because the flux that enters is equal to the flux that leaves. And it makes sense because based on Gauss's law, the total electric flux that passes through a closed object is equal to the charge enclosed divided by epsilon 0. Now there is no charge enclosed in this object, so Q is 0. And if Q is 0, the flux has to be 0.
Du willst abnehmen, dann musst du nur weniger Kalorien aufnehmen, als du verbrauchst. Wirklich? Und warum...
An insulated sphere of radius 2 meters contains 50 microcoulombs of electric charge uniformly distributed throughout the volume of the sphere. What is the electric field 1.5 meters away from the center of the sphere? How can we do this? Well, let's begin by drawing a picture.
Jadi ini ada bola gitu ya. Kalau tadi kan kita berbicara, kita belajar mengenai fluksnya ya, dan juga kita memanfaatkan hukum Gauss tadi, bahwa integral tertutup dari E dot luasannya itu sama dengan muatan yang terlingkupi. Tadi kita sudah pelajari. Sekarang ini ada an insulating sphere of radius of 2 meter contain of 50 micro column of electric charge uniformly distribusi. Ini distribusi merata di dalam volume ini ya. Kemudian what is the electric field 1.5 away from the center of daripada lingkaran itu. Kemudian yang kedua, what is the volumes of the rapat rho-nya ya, rapat permuatan volume. Kemudian di electric field pada jarak 3 dari pusat bolanya itu sendiri. Silakan dicatat aja dulu ini. Nanti juga saya berikan linknya ya, tapi sebaiknya Anda catat supaya Anda tahu bagaimana cara mengerjakannya.
So this is going to be the sphere, and it's going to have a radius, which we'll call R, and the charge is distributed throughout the sphere. If you have a conducting sphere, or a spherical conductor, the positive charge will spread out on the surface of the spherical conductor, which means that there will be no electric field inside the conductor. But we have an insulated sphere, so the charge is distributed throughout the sphere, which means that there exists an electric field inside the sphere. So let's draw an imaginary Gaussian surface represented by this yellow sphere. And R is going to represent the distance between the center and the Gaussian surface, so we can calculate the electric field at that point. Now let's use Gauss's law to come up with an equation for the electric field inside the sphere. So Gauss's law states that the electric flux, which is the product of the electric field times the area of the Gaussian surface, is equal to the charge enclosed by that surface divided by epsilon sub naught. So how can we calculate the charge that is enclosed? A simple way to do that is to use the volume ratio of the Gaussian surface compared to the actual sphere. So the charge enclosed by the Gaussian surface in yellow is equal to the total charge times the volume of the Gaussian surface, which I'll write as Vg, divided by the volume of the entire surface, which I'll leave as Vs. So Qt, I'm just going to write Q for it. That's going to be the total charge of the insulating sphere. The volume of the Gaussian surface is going to be 4/3 pi r cubed. So we need to use the radius of the Gaussian surface, or the Gaussian sphere. The volume of the actual sphere is 4/3 pi, but using the green R, or capital R. So we can cancel 4/3 pi. And so now we have the expression for the charge enclosed by the Gaussian sphere. So let's replace this particular Q with Q times R cubed over R cubed. Now the area of the Gaussian surface is simply the surface area, which is 4 pi times R squared. So this is going to be equal to Q times R cubed divided by big R cubed. So notice that we can cancel 2 of the blue R's. So what we have left at this point is the electric field times 4 pi is equal to Q times R divided by R cubed. So now let's divide both sides by 4 pi. And let's not forget epsilon. That should be in the bottom as well. So the electric field is equal to 1 over 4 pi times epsilon sub naught times Q times R divided by R cubed. Now 1 over 4 pi epsilon sub naught, that's equal to K. So we can write the equation like this. The electric field is equal to K times Q, that's the total charge in the sphere, times the radius of the Gaussian surface inside the sphere, divided by the radius of the actual sphere, cubed. So let's go ahead and use this formula to get the answer. So K is 9 times 10 to the 9. Q, which represents the total charge on the sphere, that's 50 microcoulombs, which is 50 times 10 to the minus 6. And R, the blue R, that's the radius of the Gaussian sphere, which is 1.5 meters. That's where we wish to calculate the electric field. And the green R value, that's the radius of the insulating sphere, which is 2 meters. So it's going to be 2 raised to the third power. So let's go ahead and plug this in.
Baik, dari sini ada pertanyaan.
So the electric field is equal to 84,375.
Ya, tadi ada yang pertama itu mengenai flux ya di dalam segi 4. Terus yang kedua itu apabila di dalam bola dielektrik diberikan muatan. Silakan ada pertanyaan di sini.
Saya Pak, izin
Ya.
bertanya.
Iya Mbak Diti, silakan.
Untuk yang kubus tadi itu dibagi 6 ya Pak?
Ya, kubusnya dibagi 6 Mbak.
Nggih.
Kan itu kan sebentar saya kubus itu ya dibagi 6 Mbak. Ini kan kalau saya punya kotak gitu ya. Kan itu kan muatannya, ini kebetulan bukan kubus. Enggak ada kubus. Oke lah, gini separuh ya kubus ya. Itu kan muatannya kan diletakkan di tengah. Ya, di tengah begini kan kubus ini gini. Ini diletakkan di tengah. Maka dia itu kan akan menyebar seperti ini ya. Maka yang dia akan keluar karena muatannya positif, maka dia keluar. Yang bagian atas ini tegak lurus ke sana sehingga dibagi 6. Kubus kan sisinya ada 6. Maka fluxnya itu dibagi dengan 6 untuk satu sisi. Gitu.
Nggih Pak, matur nuwun.
Silakan yang lainnya. Untuk yang bola yang diberi muatan bola begini ya, itu kan bolanya itu bola dielektrik ya. Arti dielektrik itu bisa bolanya itu bentuknya polimer. Bentar ya, saya enggak bola. Nah, ini saya punya bola. Ini ya. Ini saya ambilkan contohnya ini bola. Ini bola voli ya. Ini maksudnya ini bolanya seperti ini. Ya, kemudian diisi polimer itu maksudnya itu bisa karet ya, bisa bisa gelas ya, atau bisa juga adalah satu ya kita kumpulkan seperti ini ya, kemudian di situ diberikan muatan ya. Jadi ini kan an insulating sphere of radius jari-jarinya 2 ya. Contents artinya diberi muatan 50 mikrokolom ya. Terus dia kalau dia itu muatannya adalah isolator ya atau dielektrik, maka muatannya itu menyebarnya merata ya. Menyebarnya merata. Oleh sebab itu dari hukum Gauss tadi kan integral tertutup E.dA sama dengan Q includes dibagi dengan A. Q includes dibagi dengan epsilon 0. Ya, sedangkan Q yang terlingkupi itu adalah jumlah muatan itu pada volume tertentu, pada luasan Gauss yang ada yang warna kuning ini. Yaitu kalau dia di dalam. Makanya tadi dikatakan bahwa luasan di sini sama dengan 4/3 VR kecil pangkat 3. Gitu ya. Sedangkan luasan Gauss-nya di sini sama dengan E dikalikan dengan A. Di mana E-nya adalah E, A-nya di sini adalah 4 VR kuadrat. Ya, oleh sebab itu
Epsilon sub naught.
ya.
So how can we calculate the charge that is enclosed? A simple way to do that is to use the volume ratio of the Gaussian surface compared to the actual sphere. So the charge enclosed by the Gaussian surface in yellow is equal to the total charge times the volume of the Gaussian surface, which I'll write as VG, divided by the volume of the entire surface, which I'll leave as VS.
Terus V ini volume dan volumenya ada.
So QT, I'm just going to write Q for it. That's going to be the total charge of the insulating sphere. The volume of the Gaussian surface is going to be 4/3 pi r cubed. So we need to use the radius of the Gaussian surface, or the Gaussian sphere. The volume of the actual sphere is 4/3 pi, but using the green R, or capital R. So we can cancel 4/3 pi. And so now we have the expression for the charge enclosed by the Gaussian sphere. So let's replace this particular
Ini
Q
luasan Gaussnya adalah bola ya,
times R cube
makanya
over R cube.
4/3 VR pangkat 3.
Now the area of the Gaussian surface
Ini
is
luasan
simply
dari
the surface area, which is
bola itu
4
sendiri.
pi
Ini luasan Gauss,
times R
volume
squared.
Gaussnya. Nah, ini kan integral E dA gitu
So
ya.
this is going to be equal to Q times R cube divided by yellow sphere.
Sorry.
And R is going to just the product of the electric field time paired to the actual sphere by the Gaussian surface in yellow is equal I, but using the green R, or capital R. So we can cancel 4/3 pi. And so now we have the expression for the charge enclosed by the Gaussian sphere. So let's replace this particular Q with Q times R cube over R cube. Now the area of the Gaussian surface is simply the surface area, which is 4 pi times R squared.
Jadi ini luasan Gauss ini ya.
So this is going to be equal to Q times R cube divided by big R cube. So notice that we can cancel 2 of the blue R's. So what we have left at this point so the electric field is equal to 1 over 4 pi times epsilon sub naught times Q times R divided by R cubed. Now 1 over 4 pi epsilon sub naught, that's equal to K. So we can write the equation like this. The electric field is equal to K times Q, that's the total charge in the sphere, times the radius of the Gaussian surface inside the sphere, divided by the radius of the actual sphere, cubed. So let's go ahead and use this formula to get the answer. So K is 9 times 10 to the 9. Q, which represents the total charge on a sphere, that's 50 microcoulombs, which is 50 times 10 to the minus 6. And R, the blue R, that's the radius of the Gaussian sphere, which is 1.5 meters. That's where we wish to calculate the electric field. And the green R value, that's the radius of the insulating sphere, which is 2 meters. So it's going to be 2 raised to the 3rd power. So let's go ahead and plug this in. So the electric field is equal to 84,375 newtons per coulomb. So that's all you got to do for part A. Now what about part B? How can we calculate the volume charge density? What equation do we need? The volume charge density is represented by the symbol rho. It's equal to the total charge divided by the total volume. And the volume of the sphere, we know it's 4/3 pi r cubed. So let's go ahead and use this formula to calculate the volume charge density. So Q is 50 microcoulombs, or 50 times 10 to the minus 6 coulombs. Let's divide that by 4/3 pi times the radius of the insulating sphere, which is 2 meters, raised to the third power. So the answer that I got is 1.49 times 10 to the minus 6. And the units for the volume charge density, it's coulombs per cubic meter. So that's rho. So that's how you can calculate. So now let's take a few minutes to get the electric field inside the conductor. But instead of in terms of Q, let's get it in terms of rho. So we came up with the formula, the electric field is equal to K times Q times R divided by R cubed. And we know that rho is equal to Q over V, which means Q is the charge density, the volume charge density, times the volume. And the volume of a sphere is 4/3 times pi r cubed. So therefore, let's go ahead and replace Q with this expression. So we're going to have K times P times 4/3 pi r cubed times R. And on the bottom, we have R cubed. So we can cancel R cubed. And so the electric field is equal to K times P times 4/3 pi times R. But now let's replace K with 1/4 pi epsilon zero. So if we do that, the electric field is now equal to P, or rho, times 4/3 times pi times R. And K is 1/4 pi epsilon sub naught. So we can cancel the force and pi. And this 3 is in the bottom, so we could just put it here. So therefore, the electric field is equal to the volume charge density times the distance between the center and the point of interest inside the sphere. So keep in mind R, little r is less than big R. So you're calculating the electric field inside the sphere. And it's going to be divided by epsilon sub naught times 3. So this is the electric field inside the sphere if you're given the volume charge density. That's how you can find it. Now let's move on to the last part. What is the electric field 3 meters away from the center of the sphere? So this time we want you to calculate the electric field at a point outside of the sphere. So little r is bigger than big R in this case. So let's start with Gauss's law. EA is equal to Q divided by epsilon sub naught. So the area of the new Gaussian surface, which is indicated by the purple sphere, is 4 pi r squared. Now, the total charge enclosed by that purple sphere is the same as the total charge enclosed by the insulating sphere. There's no charge in this region. So Q is just Q. We don't have to change it. So now let's divide both sides by 4 pi r squared. So the electric field is equal to Q divided by 4 pi r squared times epsilon sub naught. So let's rewrite the equation. So I'm going to rewrite it as 1/4 pi epsilon sub naught times Q divided by r squared. So this is equal to K. So therefore, the electric field outside of the insulating sphere is the same as the electric field of a point charge. It's equal to KQ over r squared. So now let's use the formula to get the answer. So we know K is 9 times 10 to the 9. Q is 50 times 10 to the minus 6. And R, we want to find the electric field 3 meters away from the center. So let's plug it in. It's going to be 9 times 10 to the 9 times 50 times 10 to the minus 6 divided by 9. And so the electric field is 50,000 newtons per coulomb. So in this problem, we have a hollow spherical conductor. The radius of this conductor is 3 meters. Let's represent that by using capital R. And our goal is to find the electric field at the center of the sphere. The electric field inside a conductor is equal to 0. In the case of having a cavity or a hole inside the spherical conductor, it's going to be equal to 0 if there's no charge in the center. And we can use Gauss's law to explain that. Gauss's law states that the electric field times the area of the Gaussian surface is equal to the charge enclosed by that surface divided by epsilon sub naught. So let's create a Gaussian surface around the center. So that Gaussian surface has a certain value of area, but there's no charge on that surface. So Q is 0, which means that the product EA is 0. Now A has a finite value, which means E has to be 0. So if there's no charge enclosed by a Gaussian surface, then there's no electric field emanating from that region. So that's it for part A. The electric field is equal to 0 at the center of a hollow spherical conductor if there's no charge placed in the cavity. All of the charge on the conductor spreads out evenly on the surface. These positive charges want to be as far apart as possible from each other, since like charges repel. Now what about part B? What is the surface charge density in this problem? How can we figure that out? Well, the equation that we need is this equation. The surface charge density is the ratio between the charge and the area. The area is basically the surface area of the sphere, which is 4 pi r squared. So we have the charge is 20 microcoulombs, or 20 times 10 to the minus 6 coulombs. And the radius of the sphere is 3 meters. So let's go ahead and type this in. So the surface charge density is 1.768 times 10 to the minus 7. And the units are coulombs per square meter. So that's how you can find it. Now what about part C? What is the electric field at a distance 5 meters away from the center? So what's the electric field at this point? So let's use Gauss's law to get the answer. So the electric flux, which is the product of the electric field times the area, it's equal to the charge enclosed by the Gaussian surface divided by epsilon sub naught. So the Gaussian area is represented by this purple sphere with radius r. So the surface area is 4 pi r squared. Now the total charge enclosed by the purple sphere is equal to the charge enclosed by the original sphere, because there's no charge in between. so we don't have to change Q. We can leave it the way it is. So now let's divide both sides by 4 pi r squared. So it's Q divided by 4 pi r squared, epsilon sub naught. Now I'm going to rewrite it like this. 1 over 4 pi epsilon sub naught times Q divided by r squared. 1 over 4 pi epsilon sub naught is K. So the electric field is the same as calculating the point charge. It's K times Q divided by r squared. So K is 9 times 10 to the 9. Q is 20 times 10 to the minus 6. And the radius, in this case, is 5. We want to find the electric field 5 meters away from the center. So the electric field is equal to 7,200 newtons per coulomb. So that's how you can find it outside of the hollow spherical conductor. You can treat it as if it's a point charge. Now let's say if we have another hollow cylinder. I'm going to make it bigger this time. And let's say there's a charge at the center. Let's use a negative charge. So we have a negative point charge with a magnitude of, let's say, 8 microcoulombs. And let's say the charge on the spherical conductor, let's say it's 15 microcoulombs. Based on this information, what is the charge on the interior of the spherical conductor and on the exterior of it? And also, how can we calculate the electric field? Let's say at a distance r from the point charge and at another distance r at the midpoint of the spherical conductor and also outside of it as well. So let's call this R3
Maaf Pak, share screen-nya belum muncul.
and R1.
Belum ya? Bentar, Mas.
And also, how can we calculate the electric field? And let's say the charge on, let's use a negative charge. 7,200 newtons per coulomb. So we have a negative point charge with a magnitude of, let's say, 8 microcoulombs. And let's say the charge on the spherical conductor, let's say it's 15 microcoulombs. Based on this information, what is the charge on the interior of the spherical conductor and on the exterior of it? And also, how can we calculate the electric field? Let's say at a distance r from the point charge and at another distance R at the midpoint of the spherical conductor, and also outside of it as well. So let's call this R3, R2, and R1. Let's say R1 is 1 meter, R2 is 3 meters, R3 is 5 meters. Actually, instead of using numbers, we'll just write the generic equation. So what is the charge on the interior of the conductor and on the exterior? So first, let's draw a line to separate the interior part of the spherical conductor and the exterior part. Now, because we have a charge on the inside that's -8, and the opposite charge will form on the interior of the conductor. And it's going to be equal in magnitude to this charge. So it's going to be positive 8 microcoulombs. Now the total charge on the sphere is 15. So if 8 rests on the inside, 7 has to rest on the outside, because 8 plus 7 is 15. So in this particular example, we have a positive charge on the inside and on the exterior of the spherical conductor. So now let's talk about how to calculate the electric field. The setup is the same as the last example. If you follow the same process, you'll come with this equation, KQ over R squared. But if you want to go through the process, it's EA is equal to Q enclosed divided by epsilon sub naught. So that's going to be Q divided by 4 pi R squared epsilon sub naught, if you want to use that process, but it's the same as using this equation. Now let's talk about how to calculate the electric field at R1. So you have to ask yourself, if we draw a Gaussian surface at R1, what is the total charge enclosed? The total charge enclosed is the -8 microcoulombs that we see here. So therefore, the electric field at R1 is going to be K times the -8 microcoulombs, which we'll just plug in the magnitude only. So that's 8 times 10 to the -6. K is 9 times 10 to the 9. And then whatever R1 is, you just plug it in. So you know how to finish it. Now, if you wish to calculate the electric field at R2, we need to find the total charge enclosed by the Gaussian sphere, which is the yellow line. So we have a charge of -8 plus 8, so the total charge is 0. And if Q is 0, then the E value is 0. Let's call that value E2. So E2 is 0. Now E3 is going to be K times Q. That's the total charge. So these two cancel. The total charge is 7. You can also get that number by adding -8 plus 15. So it's going to be K times 7 times 10 to the -6 divided by R3 squared. So that's how you can calculate the electric field outside of the hollow conductor, if there's a charge on the inside. So you got to find the total charge. You have to add these two values.
Laut Charlie war einst ein Holzfäller. Er erlegte die wilden Wölfe.
Oke, ini apa namanya? Saya ingin
In this video, we're going to focus on calculating the electric field due to a charged disk. We're going to derive the formula, and from that formula, we're going to come up with a formula to calculate the electric field of an infinite sheet of charge, and also the electric field between two parallel plates that contain a sheet of charge, an infinite sheet of charge. So we're going to do both of those, actually all three of those concepts in this single video. So let's go ahead and begin. So let's start with a disk. Now this disc is completely solid throughout. There's no open hole in the center. It's not a ring, but I'm going to draw an inner circle. We need to distinguish the inner radius and the outer radius. My circles are not perfect, but let's see if I can do that one more time. Okay, I'm just going to work with it. So our goal is to calculate the electric field from the center at some point P. So this is the inner radius, which I'll denote as lowercase r. And this segment here, that's going to be dr. So the inner radius is r, the outer radius is r plus dr. Now from this point to point P, let's call it L. And x is the distance between the center and point P. Now let's say if we have a small amount of positive charge in this region. That small positive charge will have a charge of dq, and you could treat it like a point charge. The electric field created by a point charge is equal to k times q divided by r squared. In this case, L squared, since L is the distance between this small segment of charge and point P. Now, that small segment of charge, dq, will create an electric field at point P known as dE. So dE is going to be k times dq divided by L squared. Now, at point P, the electric field is directed in this direction. However, it has an x component, EX, and it has a y component, EY. Now, EY is directed in a negative x-axis for a charge on the top. For charges on the bottom, it will create an EY that is directed in the positive y-axis. So these two vectors will cancel, and therefore the net electric field in the y direction will be equal to 0. So EY is 0. EZ is also 0. It turns out that the net electric field at point P is equal to the x component of the electric field. So therefore, we need to calculate dE sub x. dEx is basically dE times cosine theta, where theta represents this angle. It's also equal to that angle. And here's the electric field E. So what is cosine theta? Cosine theta, according to the SOHCAHTOA thing, is equal to the adjacent side divided by the hypotenuse. So in this case, it's the ratio of x divided by L. So at this point, we can replace dE with the equation that we have here. We can get an expression for dEx. So dEx is dE, which is k times dq divided by L squared, times cosine theta, which is x divided by L squared. I mean, not L squared, but just x over L. Now, according to the Pythagorean theorem, we have a right triangle. L is basically the square root of x squared and r squared. So that expression will be useful shortly. So we can see that dEx is equal to k times dq times x. Divided by L to the third power. So keep this equation in mind. We're going to refer back to it. Now for the circle that we have, the area is equal to pi r squared. This is the area of any circle. Now, according to the Pythagorean theorem, we have a right triangle, L to the third power. So keep this equation in mind. We're going to refer back to it. Now, for the circle that we have, the area is equal to pi r squared. This is the area of any circle. So if we differentiate both sides, the derivative of a, or the differential of a, is dA. The derivative of r squared is 2r times dr. So we can say that dA is equal to 2 pi r times dr. So it's equal to the circumference, 2 pi r, times the width between the large circle and the smallest circle. Now we need to talk about sigma, which is basically the ratio between the charge and the area. So it's Q over A. And so for the small segment of charge that we had here, we could say it's equal to the dQ over dA. The unit of sigma is basically coulombs per square meter. So if we rearrange this equation, if we multiply both sides by dA, we're going to get this expression. Sigma is equal to, well, dQ actually, is equal to sigma times dA. So what we're going to do now is replace dA with 2 pi r dr. So dQ is 2 pi r times sigma times dr. So now we can replace this dQ with this expression. So now let's replace dQ. So dEx is going to equal K times X times sigma times 2 pi r dr. Divided by L cubed. So if we integrate both sides, the integral of dEx is simply equal to EX. Now all the constants we're going to move to the front. And for the circle that we have, we're going to integrate it from the center to the outer edge of the large circle. So that's from 0 to r. K is a constant. X, the distance between the center and point P, that's not going to change. As we integrate it from 0 to r, x is going to be constant. So we can move x to the front of the integral. Sigma is constant. That's the charge per unit area. And the 2 pi term is constant. So we have r dr. Now we know that L is equal to the square root of x squared plus r squared. So it's x squared plus r squared raised to the 1/2. So if we cube both sides, 1/2 times 3 is 3 over 2. So L cubed is x squared plus r squared, that's a terrible 2, raised to the 3 over 2. So now that we have that, what we're going to do at this point is we're going to focus on finding the antiderivative of this expression. So just jot this equation down, and we're going to come back to it. So let's integrate r dr over x squared plus r squared raised to the 3 over 2. So we're going to use the U substitution technique. So U, let's set it equal to x squared plus r squared. Since we have dr here, r is the variable, x will be treated as a constant. The derivative of any constant, like x squared in this case, is 0. So it's going to just disappear. The derivative of r squared is 2r times dr. So solving for dr, dr is du divided by 2r. So this is going to be r divided by u raised to the 3 over 2. And let's replace dr with du over 2r. So we can cancel the r variable. And the 2, let's move it to the front. Since it's on the bottom, it's equivalent to 1/2. Now we're going to take this u variable, move it to the top, which will change the exponent of positive 3 over 2 to negative 3 over 2 times du. So the antiderivative of u to the negative 3 over 2, you need to add 1 to negative 3 over 2. Negative 3 over 2 plus 1, which is the same as negative 3 over 2 plus 2 over 2, is negative 1/2. And then you need to divide by negative 1/2, which is equivalent to multiplying by the reciprocal of negative 2 over 1. So we can cancel the 2's. And what we have left over is negative u to the negative 1/2, which we can move the u back to the bottom. So it's negative 1 over u to the half, which is negative 1 over the square root of u. Now let's make some space. Let's get rid of a few things. At this point, we can replace u with x squared plus r squared. So this is equal to negative 1 divided by the square root of u, or the square root of x squared plus r squared. So now let's begin with our expression that we had last time. So ex, which we said was equal to 2 pi k times x times sigma integral from 0 to r divided by x squared plus r squared raised to the 3/2 dr. So this portion is equal to this expression evaluated from 0 to r. So ex is now 2 pi k times x times sigma, which is the charge per unit area. And then we have negative 1 divided by the square root of x squared plus r squared, evaluated from 0 to r. So we're going to begin by plugging in the top number. We're going to replace capital R. We're going to replace lowercase r with capital R. Lowercase r is the variable, x is the constant. So we can't replace the constant here. So if we plug in capital R, it's going to be negative 1 over the square root of x squared plus capital R squared. Now let's plug in 0. Let's replace lowercase r with 0. So it's minus negative 1 divided by the square root of x squared plus 0 squared. These two negatives will change into a positive. So we have negative 1 over the square root of x squared plus r squared, and then plus 1 over the square root of x squared. The square root of x squared is simply x. And since this is positive, I'm going to move it to this side. So I'm going to switch these two. So the electric field in the x direction is therefore equal to 2 pi k times x times sigma. And let's put this term first. So that becomes 1 over x minus 1 over the square root of x squared plus r squared. So what we're going to do now is we're going to take this x and move it in to the brackets. We're going to distribute it to the two terms inside. So x times 1 over x, the x variables will cancel, and you simply get 1. So ex is now 2 pi k times sigma, x over x is 1, and x times what we have here, the x is just going to move to the top. So it's x divided by square root x squared plus r squared. So this is the equation in terms of k. And keep in mind, k is 9 times 10 to the 9. I believe it's like 8.99 times 10 to the 9, but you could round it to 9 times 10 to the 9. Now, most textbooks would write this formula in terms of epsilon sub naught. And k is equal to 1 over 4 pi epsilon sub naught. Epsilon sub naught is about 8.85 times 10 to the minus 12. So let's go ahead and replace k with this term. So the electric field in the x direction is now equal to 2 pi sigma times 1 over 4 pi epsilon sub naught times this stuff. So we can cancel the pi and the 2. 2 over 4 is basically 1 over 2. So now that gives us this expression. The electric field is now equal to sigma divided by 2 epsilon sub naught times 1 minus x over the square root of x squared plus r squared. So now let's apply this information in a problem. A disk of radius 3 meters contains a total charge of 480 nanocoulombs. What is the charge per unit area? So let's draw a picture first. So here we have a charged disk, and r is the radius, and some distance away from the disk, let's say point P, we wish to calculate the electric field, which we know is going to be directed along the x-axis, away from the center. Now the distance between the center and point P is 25 centimeters. Keep in mind this picture is not drawn to scale. So with this information, how can we calculate the charge per unit area? So let's write down what we have. So we know that R is equal to 3 meters. The total charge Q is positive 480 nanocoulombs. And X is 25 centimeters or 0.25 meters. Now sigma, which represents the charge per unit area, is Q divided by A. The area of the disk is basically pi r squared. So therefore, the charge per unit area is going to be 480 times 10 to the negative 9 coulombs. Nano is 10 to the minus 9, divided by pi times 3 meters squared. So let's go ahead and calculate the answer. So let's type in what we have. The answer that I got is 1.697 times 10 to the negative 8 coulombs per square meter. Hopefully you got the same thing. Now that we have the charge per unit area, let's go ahead and calculate the electric field. So what equation do we need? We can use the equation that we came up with a a few minutes ago, particularly this form. It's sigma divided by 2 epsilon sub naught times 1 minus x divided by the square root of x squared plus r squared. So now we just gotta plug it in. So sigma is 1.697 times 10 to the negative 8, which got cut off, divided by 2 times epsilon sub naught, which is 8.85 times 10 to the negative 12. And then it's 1 minus x. X is 0.25, divided by the square root of x squared, 0.25 squared, plus r squared, which is 3 squared. So you can type this whole thing in a calculator, but for those of you who may not have an advanced calculator, I'm going to do most of this step by step. So 1.697 times 10 to negative 8 divided by 2 and 8.85 times 10 to the minus 12. So this section right here, that's equal to 959.1. 0.25 squared plus 3 squared, that's about 9.0625. The square root of that, it's 3.0104. 1 minus 0.25 times 3.0104. That's about 0.91695. So you should get a final answer of 879.5 newtons per coulomb. Now, it turns out that we can actually get the equation to calculate the electric field produced by an infinite sheet of charge. Even though we're starting from a disk, if we increase the radius of the disk such that this object becomes infinitely large, the shape of the object is no longer important. It turns out you can still get the right equation to calculate the infinite sheet of charge, or the electric field created by an infinite sheet of charge, starting with this formula. So let's go ahead and do that. Now, as the disk becomes very, very large, we need to realize that R approaches infinity. So let's focus on this expression. What is the limit as R approaches infinity for the expression x divided by the square root of x squared plus r squared? Now keep in mind, x is a constant. So if we replace r with infinity, what's going to happen? So we're going to have infinity squared. A finite number plus an infinite number is going to be an infinite number. If you add, let's say, 5 squared plus 1,000 squared, 1,000 squared is about 1,000,000. 5 squared is 25. 25 plus 1,000,000 is 1,025,000, which rounds to 1,000,000. So x becomes insignificant. So we can say this is approximately equal to the square root of infinity squared. The square root of a number squared is equal to that number. And if you take a finite number and divide it by an infinite number, or if you take a small number and divide it by a large number, it's going to approach 0. For example, 10 divided by 1,000 is 0.01. 10 divided by 1,000,000 is even smaller. That's like 0.00001. So this approaches 0. So as r becomes very large, this term approaches 0. So Ex is now equal to sigma over 2 epsilon sub 0 times 1 minus 0, which is therefore equal to sigma over 2 epsilon sub naught. So this is the electric field created by an infinite sheet of charge. And that's the equation. Go ahead and try this problem. What is the electric field produced by an infinite sheet of charge that has a charge per unit area of 5 microcoulombs per square meter at a distance of 50 centimeters and 5 meters away from the center of the plate? So let's draw a picture. So we're going to draw a very large rectangle. And that rectangle has a positive charge that is distributed uniformly around the plate. We wish to calculate the electric field at some point P. So initially at 50 centimeters away. So the equation that we can use is this equation, the electric field, which is directed away from the plane of the plate, in this case, in the x direction. The plane of the sheet of charge is in the YZ direction. It's in the YZ plane. So the electric field is perpendicular to the YZ plane. So it's in the x direction. And it's equal to the charge per unit area divided by 2 times epsilon sub naught. So we have the charge per unit area. It's 5 microcoulombs per square meter, or 5 times 10 to the minus 6 coulombs per square meter, divided by 2 times epsilon sub naught, which is 8.85 times 10 to the minus 12. So it's a very simple formula to use. So I got 2.82 times 10 to the 5th power newtons per coulomb. So that is the electric field produced at some point P. Notice that for this equation, we didn't have to plug in the 50 centimeters or the 5 meters. The electric field is independent of the distance between the plate and point P. Since the plate is infinitely large, x is insignificant. So the distance doesn't matter. There's no x in this equation when you have an infinite sheet of charge. So the electric field is simply sigma divided by 2 epsilon sub naught. So it's independent of the distance. So for part A and part B, the answer is the same. Now, what is the electric field between 2 infinite sheets of charge? So let's say if we have parallel plates, one is negative and the other is positive. So what is the electric field inside between the 2 plates and outside of it? Let's call this sheet 1 and sheet 2. So sheet 1 will create an electric field that is directed away from the positive charge. So let's call that E1. Sheet 2 will create an electric field that is directed towards the negative charge. As you recall, the electric field always emanates away from a positive charge, but towards a negative charge. So the electric field created by sheet 2 is going up towards the negative charge. So as you can see, the net electric field between the 2 plates is the sum of E1 and E2. Now what about above the negatively charged plate? The electric field created by the positively charged plate will still be in the upward direction because it's going away from the positive charge. E1 will continue to go this way. And what about E2? The electric field created by the negatively charged plate is directed towards the negative charge. So at a point above the negatively charged plate, it's going to go towards it, so it's going in a downward direction. Now, because the electric field of an infinite sheet of charge is independent of the distance, E1 and E2 have the same magnitudes. So the net electric field, which is the difference between E1 and E2, is going to be 0. If you have two numbers that have the same value, and if you subtract them, it's equal to 0. 10 minus 10 is 0, 5 minus 5 is 0, so the net electric field outside of it is 0. The same situation applies below the positively charged plate. E1 is going to emanate away from the positive charge, so it's going in the negative y direction below the positively charged plate. E2 is directed towards the negatively charged plate, and so it's in the positive y direction. So the net electric field is going to be E2 minus E1, which, because they're the same, it's still equal to 0. So whenever you have two infinite sheets of charge, the electric field outside, above it and below it, is equal to 0. However, the electric field inside is the sum of these two values. Now we know that the electric field due to one infinite sheet of charge is the charge per unit area divided by 2 times epsilon sub naught. So therefore, the net electric field, which is the sum of the electric field of two infinite sheets of charge, is going to be E1 plus E2, or sigma divided by 2 epsilon sub naught, plus another sigma divided by 2 epsilon sub naught. Sigma. And so we can cancel the 2. 2 divided by 2 is 1. And so the net electric field in between two infinite sheets of charge is simply the charge per unit area divided by epsilon sub naught. So you know how to use this equation in the problem. So that is it for this video. Thanks for watching and have a great day.
Baik, jadi tadi kita sudah bahas ya, mulai dari hukum Gauss, kemudian kita perhatikan bahwa integral tertutup dari E dot dA atau EA gitu sama dengan Q muatan yang enclosed ya, yang dilingkupi dibagi dengan epsilon 0. Jadi kita juga pakai mana kalau infinited dan sebagainya. Jadi nanti kuisnya sampai materi hari ini ya. Jadi mulai dari yang analisa vektor sampai dengan hari ini. Oke, saya kira sampai di sini, sampai ketemu hari Jumat kuis pertama, gitu ya. Ya, assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam, terima kasih Pak.
Terima kasih Pak.